Hey everybody, and welcome back to Linear Algebra Online. So this is our second course review video here. And just like last time, I'm picking out problems that I think are going to be really important for you to know for the final exam for the course. So this first one just says that let capital pi here be the plane in R3 spanned by these two vectors, all right? And we want to extend it to an orthonormal basis for R3. Anytime you're seeing this kind of thing where you're extending to an orthonormal basis, you want to think Gram-Schmidt, right? And you can see right now these two vectors are not perpendicular. Definitely not like 1, 2, but you know, if you just dotted them, you'd get -1 plus 4. So they're not perpendicular, so we're going to also have to make these perpendicular to each other. And, you know, kind of the idea right now is like, so we can we can pick one of these as like one of my, you know, my final like orthogonal vectors. So let like, oops, I didn't even write. Let like v1 equal like x1. So I'm going to kind of build off of that one. You know, that honestly, it probably actually is smarter to build off of this one because it's got a 0, but I already wrote it, so I'm just going to build off of that one. So, you know, the idea here is like if you've got, you know, v1, it's kind of just easier to draw this in a plane, but, you know, obviously this is happening in 3D. And then we have like x, so this is, v1 or like x1, and then this is, you know, some x2 that's not perpendicular here, you know, to x1. The way that we can kind of start off this process is we can take x2 and then minus off the projection vector here onto v1. And then those two things will give me another, if you combine them, right, you'll get a perpendicular vector. So like this down here, you know, is roughly the projection of x2 onto v1. And so if you just minus off that projection, so you're going like that way, right, then this new yellow vector, right, is what my v2 will be, and v2 will be perpendicular to v1. That's really like kind of how Gram-Schmidt works in like 2D. And then we basically will do that for a third vector, and we have to do 2 subtractions because we're going to kind of work off of the 2 vectors that we have that are already perpendicular. And you kind of like position all of them by doing these like subtractions, these projections, and then you will get 3 perpendicular vectors, and we can normalize them at the end and stuff like that. So we also need to have another vector eventually, but let's just deal with that later, I guess. So this v2 that I'm talking about is going to be x2 minus the projection of x2 onto v1. And, you know, so a lot of this stuff is pretty straightforward computation stuff. You got -1, 0, 2 is x2 minus, if you do that dot product stuff out, you get minus, well, you get 3/9, and then you get 1, 2, 2 here. And if you do all that out, you will get -4/3, -2/3, and 4/3. And, you know, a lot of times in these problems you want to, like you will need to normalize things, but you can scale this right now, and we just need to find the direction part of v2 first. That's the more important thing. So definitely scaling by like 3 and getting rid of the fractions would be nice there. But you don't have to do that. You can leave it in too. For the next vector, for like v3, getting that, we're going to need to let there be another vector like x3 here. So you just need to get something that's not in line with the plane that you get from the span of these two. And so there's lots of things here, but you should always try to pick like easy ones. Like 0, 0, 1 is one that you can kind of clearly see is linearly independent from these two. But if you're not sure, you can always like make a matrix, REF the thing, and hopefully you get that diagonal kind of one. I get the identity matrix, right? So this is what I'm going to use for calculating my V3. So V3 will just be x3, that vector that I just got there, minus x3 projected onto V1, and then minus x3 projected onto V2. And, that's just the general structure of Gram-Schmidt. It just keeps going. So, like, I never really make you do a bigger one than 3 dimensions, but if you did have to go to 3 dimensions, you just do another projection, minus another projection, minus another, you just keep going. So again, pretty straightforward stuff. 0, 0, 1, minus, if you do that, dot product computation there, you get 2/9, and then 1, 2, 2. This one is a third, and then that's negative 4/3, negative 2/3, 4/3, which I'm not scaling it, but I definitely could to make it a little easier. Either way, you're going to add all this up. I use a calculator for a lot of this stuff. I get 2/9, negative 2/9, and a 9th. And it's always good when you're doing Gram-Schmidt things to check that, all your dot products are actually going to give you 0. Sometimes they're a little easier to tell, but, like take these ones here. 1 times that, so you got 2/9, and then you got minus 4/9, right? So now you're at negative 2/9, and then you have plus 2/9. So that one definitely, you can see zeros out. Check this one with this one, you will get it. And this one with this one, you'll get it. So that's always a quick little thing to just kind of make sure that, you don't have any issues at this point, because you don't want to get into normalizing them unless you've got the right vectors. For the normalizing part, we just got to find all the magnitudes. So magnitude V1 is 3, magnitude V2 is 2, and magnitude V3 is a third. And so my final answer, let's use W's, I guess. So W1, one of my vectors, my orthonormal basis, is just a third of V1. W2 is 1/3 this negative 2, negative 1, 2 vector. Just dividing this by 2, and then I took a third out. And then W3 is 1/3 times 2, negative 2, 1, right? Just taking a third out of here, yeah. And so, so these 3 vectors will be an orthonormal basis for R3. And this becomes really important when you're starting to do a lot of stuff in higher courses where you're basically given new, the basis that you could be given is not perpendicular, but you want to set up certain computations that are really nice. And they're going to be nice if you have perpendicular basis vectors. This becomes a super important trick, this Gram-Schmidt thing. Definitely a good thing to know. All right, this problem I just kind of created because I think one of the more important parts of linear algebra is having some sort of intuition about what a matrix is doing. I honestly don't think I did well with this until quite a bit later on. In the beginning, I just looked at these things as tables with numbers and didn't really think much about it. And I could manipulate them and do things, but if you have an intuitive idea about what a matrix is doing, things like analyzing the kernel become a lot more intuitive, quicker. Just a lot of stuff makes more sense. So it's good to know what different matrices are doing, just generally speaking. So all of this comes down to knowing that this column is where I hat lands after a transformation, and then this column is where J hat lands. And this could extend to higher matrices too, but it's definitely easier to think of 2 by 2 ones. So if you think about this, right, it's saying that I hat really just lands where I hat is, but j hat goes to, minus j hat, right? Minus j hat. And so if you think about a picture like, the xy axis, basically we're taking like a little square like this, and this transformation would flip, so this would stay put, right? But, things like this vector would flip to here. Things like this vector, which is truly j hat, right, would flip to here. And so you would get this kind of, little square after the transformation. You can see that basically what that means is this transformation t is like a x-axis flip. And, the rest of these you can do the same kind of way. I highly suggest you pause the video, think about what these different transformations are, and then also be able to visually interpret kind of what they would look like. These things, and just up here I'm saying think of a 1 by 1 square in just the first quadrant, because depending where you draw the square, you can get different things, but just think first quadrant. So all of these, these kind of things, these matrices on this level are ones that I would hopefully you would be able to interpret on a final exam just intuitively without, much else to analyze it. Just thinking literally this part about where the basis vectors line up. So the next one is, I hat is going to j hat's going to I hat. So there's a flip again, but this time it's going to be a flip over the line y equals x. And so, literally the square, this little 1 by 1 square right here, since it is already symmetric on y equals x, you actually would just stay put right there, okay? This next one is a little weird maybe. It's saying j hat, stays the same. You can see that. But I hat is sort of getting either squished a little, there's the term is actually shear, is what I want to say. But, if you think 1, 2, it's taking I hat and going and kind of shearing it, stretching it up to 1, 2. Even 1, 1/2, or 1 and 0.1, basically it's moving the basis vector I hat up off of the x-axis. And in terms of this piece, it's going to kind of give you a rhombus-y kind of parallelogram sort of shape. And so we would call these things vertical shears, all right? And what it sort of would give you, so didn't give myself a lot of room here. So there we go, perfect. This would give me sort of this shape. So you would have this vector, this vector staying put, j hat staying the same, but then the I hat, would kind of be stretched up, so it would still end at 1, and that's kind of roughly what you got. But it would sort of be taking this square and just smushing it up, and you're going to get a parallelogram looking thing like that. And then we'd call that a vertical shear. This one, again, j hat's not changing, so you're not doing really anything in the y direction there, but you are shrinking in a sense, right? Because k is a fraction between 0 and 1. You're shrinking it, as k gets smaller and smaller and smaller. So this is some sort of horizontal compression. So we would basically get something like this. If this was 1, let's say, and like k is maybe halfway or whatever, that's kind of the box I started with, and we would have that sort of thing. So it would, in a sense, be squishing, the box over, and you could get like a super small little rectangle and things like that. Last one here. Now, again, j-hat's the same. Maybe I was too boring with that in a lot of these problems at the end here. But I-hat is, so you're going to negative I-hat, right? And so you're taking, I-hat and you're flipping it to negative. So this one's probably pretty easy to see that it's a y-axis flip this time. Oops, y-axis flip. And so it would look like this. It would just take your box that was over here and you're just flipping it over the y-axis. So definitely can get really complicated if you start putting numbers everywhere and whatnot, but I think these are good teaching examples for what intuitively a matrix is doing. Always just look at it as, where does I-hat go, where does j-hat go? All right, so we did one of these problems in the last video, but this one's got two things that are a little different about it, and so I think it's good to do another one of these. And also, it's a really important concept from this course. So we have this matrix, and the question is just, is A diagonalizable? And if it is, diagonalize it. So one of the things that's different is it's a upper triangular matrix, and so these are really easy to find the eigenvalues for. It really just comes out of like the computation for the determinant, but the eigenvalues will just be the things on the diagonal. So you have like lambda 1 and 2 equal 1, and lambda, let's say 3 equals 4. And notice that this one has algebraic multiplicity 2. This one has algebraic multiplicity 1, but that's not interesting for this problem. And so if we were going to compute the eigen vectors now, right, you're going to just basically set up the determinant, right? Let's do lambda 1 here. So a minus 1i augmented with 0. We're going to, sorry, I don't want to take the determinant of that. I want to REF that thing. And so that would be the REF of 0, 1, 0, 0, right? 0, 0, 1, 0, 0, 0, 3, 0. And if you do that out, you're going to get 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. And so this is saying that, like x2 in there equals 0, which also x3 equals, but like x1 is free. And so the eigenspace here for lambda equals 1 is the span of the vector 1, 0, 0. And this is the other thing that's different. In the other video, the matrix was diagonalizable, but here this thing has geometric multiplicity 1, and 1 is not equal to 2. The 2 that matters is, of course, this 2. And so that 2. And so that's like a really important theorem in linear algebra. Like the idea is basically if you went to go try to create this matrix P, that should be invertible. You could put in 1, 0, 0 as one of the columns in there, but you would really want to put in another one because you need this to kind of relate to lambda 1 here, and lambda 2 is also 1 there. Lambda 3, sorry, which is equal to 4, but lambda 3 would give us something here, so that part would be okay. This is the one that we would not be able to get, and then you would basically have a non-square matrix that you couldn't even take the inverse of, and things like that. So, so this thing is not diagonalizable, definitely something you want to know about, regarding different matrices and how you compute that and stuff. All right, just going to do probably one more problem in this video. So this transformation T was supposed to be superscripted. Imagine that says R2 to R2. Is just the rotation transformation. So it just rotates every vector in the plane by an angle theta. And the question is this map one-to-one and onto, all right? And so, there's a few ways we can go about this. We have all sorts of results with transformations and analyzing whether they're one-to-one onto. One of the most important things is that if your map is linear, and say you get that it's one-to-one, then you'll get onto for free. Or if it's linear and you show that it's onto, then you'll get one-to-one for free. So it actually is pretty cumbersome to show linear here. You really have to go through a lot of trig to do it, but I'm going to kind of just sketch the idea of it. So let's say we have V, okay, let's go U. And then we have another vector, V, all right? If we do just U plus V in like we could probably just fit it here too. So if we do U plus V, we're going to go U and then like plus, actually I'm going to shrink my V. We're going to go like that. So we're going to go through U and then we're going to go through, like V is maybe more like that, right? So this vector right here, right, is roughly U plus V. So if you do U plus V rotated by theta, just arbitrary theta, let's just say that's my theta, certainly this is then going to be T of U plus V, right? And you could also rotate, U by theta, right? I'm just kind of approximating, it's right there. And then you could also rotate V by theta. And what you would get is you would basically get, U, I didn't do so well there. And then V is coming out here, but we're going to do T of U plus T of V. And so you can see that it basically would end up right there. So it's definitely not a rigorous proof, but I'm giving you the intuition that basically the sum should work out nicely. The other one's a little easier to kind of show the intuition for, the other one being the scalar piece. So if you let this be like U, okay, you can do the transformation of U by like some theta and get, T of U. And then we could scale that by some sort of like alpha or whatever, and maybe it shrinks it to there. Or, right, you could have shrunk U right off the bat, so this is alpha times U, and then you do your transformation, right, and you would be right back to that spot. So the scalar one is probably a little more intuitively easy to see. And to actually rigorously show this, I actually remember having to do this once. It's pretty annoying because you have to like go through a lot of triangle trig, and like that's probably the best way to do it. But you have to use like law of sines and cosines, and there's like a lot to do there that I don't want to get into in here. So intuitively, I'm gonna use that as not a proof because it's not a proof, but I'm just going to be like, hey, look, T is linear, okay? Sort of, because I didn't prove it. So then let's just say I have that T is linear. I've argued it at least a little bit, right? So let, I guess, 0 equal t of v. And then in that case, right, note that v must be the 0 vector. So the kernel of this transformation just basically has to be the trivial vector. And that's just because, like, as you know, the only way I'm ever going to get the 0 vector right here from rotations by angle theta is if I was just rotating the 0 vector, right? Anything else is going to give me something that's not the 0 vector, right? And so then I can use this really important theorem from this course that says, since t is linear and the kernel of t equals 0 vector, this implies t is 1 to 1. Now, we can also say, since t is linear and 1 to 1, it must also be onto. Intuitively, it makes sense that it would be onto because every vector in the plane comes from some rotation of another vector, right? It wouldn't make sense that you wouldn't hit all of R2 using rotations. Rotations would have to hit everything, so that's what it means to be onto. So this kind of thing, we're analyzing a transformation, is a really important thing in this course. You better be able to, really formally actually prove something's linear, and I wouldn't give you one this hard. But you got to show those two things, that scalars, you can do transformation of the scalar or the scalar of the transformation, and those are equal. And also t of u plus v is equal to t of u plus t of v. And then also knowing these theorems that I'm using here for the one-to-one and onto stuff, that's also really important. So lots of stuff in this video that you definitely want to know.